before that were to happen, I'm really now getting worried about my base metal, right? Well, am I going to lose my base metal even before I develop the strength of the fillet weld? So I need to make sure that the base plate has the right amount of strength. So how do I understand that? How do I explain that? Well, let's take an example for a very simple situation. You've got a nice wide flange section, flanges and a web and everything. And to that, I'm going to attach a shear tab. Not that uncommon. Can happen, right? I'm attaching a shear tab right at the center. Right? So if you were to look at a 3D rendering of it, you would see something like this. You would see the wide flange, and you would see the shear tab in the middle. And this shear tab is welded, fillet welded in this case, to the flange. So the concern I have is that as I subject it to shear forces, I have the possibility that I need to investigate that I'll have shear failure in my base metal. Well, what kind of shear failure? Well, I could have shear yielding, or I could have shear fracture. Well, what's the difference between the two? Well, first of all, one will use 0.6 Fy, the other will use 0.6 times Fu. That's the difference in the strength. But then why would I consider them both? Isn't Fy always less than Fu? So I should just worry about shear base metal yielding. Why am I worrying about shear base metal fracture as well? Should I only be worried about shear base metal yielding? Let me draw a picture and then I'll ask you the question again. This is the shear tab in cross section. I have welded it, and that's what that, let's say that weld looks like. It's dimension of A. When I'm talking about shear base metal yielding, I can have that yielding occur across that plane. Does that make sense? And I would say that 0.6 times Fy times the thickness times the length of the weld is what I need to worry about. Fair enough? When I look at my shear fracture limit state, what it's going to do is it's going to gouge out the element right here. Right? Shear fracture is going to gouge out that portion of the base metal. So I would have 0.6 times A times Lw times Fu. Does the A make sense? Or won't I have two of them? Right? Won't I have two of them? Because I'm worried about the weld metal gouging out the base metal, causing a shear fracture along that plane. Well, that's good, but I got to make sure that 2A does not become greater than T, because T is really the maximum that I can get. Does that make sense to you? Imagine where this shear tab was really thick. Right? Put in a shear tab that was crazy thick. But then I put in a fillet weld that was really small. Now it makes sense, right? What we're talking about? We're talking about the fact that you're going to gouge out this material, which will be A times 0.6 Fu multiplied by Lw multiplied by 2. But you got to make sure that the plate is not thin enough that that 2A has now coalesced onto just the thickness of the cross section. Right? So I had 2A here, but I had the thickness here, and I got to be careful how I calculate the limit state for the base metal yielding and the base metal shear fracture. When I look at my specification, it gives me little to no guidance. It tells me use the area of the base metal. It doesn't tell me how to calculate the area of the base metal. And the book does it a little bit differently than what I'm talking about here. If I look at my table here, it just asks me to use the area of the base metal ABM. It doesn't tell me how to calculate the area of the base metal. And the book does it a little bit differently. So if you come back to my notes here, typically you will be working with the thickness times 0.6 Fy times Lw. If shear yielding governs, then shear fracture becomes irrelevant, because 0.6 Fy will always be less than 0.6 Fu, right? Unless 2A is smaller than T, in which case shear fracture could be a different strength that you need to take into consideration. Did that make sense? So if 2A is less than T, then shear yielding of the base metal will be governing, which means that my base metal strength will be given by 0.6 times Fy times the thickness of the base metal multiplied by multiplied by Lw, the length of the weld. And what's the phi factor for this? What's the phi factor for this? Well, it was on the screen a moment ago, right? So all of this is described in the specification as well. What you'll notice is that it gives you a nice picture, in the notes as well, gives you a nice picture, very similar to what I talked about here. Tells you that the strength of the base metal depends upon the minimum of 2. In this one, it uses, for base metal yielding, it uses a phi factor of 1.0 times 0.6 times Fy times T times Lw. For base metal fracture, it uses a phi factor of 0.75 times 0.6 times Fu times A times Lw. So it makes that substitution and lets you calculate the strength of the base metal for both shear yielding and shear fracture limit states. The phi factor here is 1.0. When you are looking at shear yielding, when you are looking at shear fracture, this is multiplied by 0.75 because it's a fracture limit state. Of course, the area of the base metal that you use for these calculations is something that you need to configure and understand for each weld detail. And that's why the specification doesn't give you a simple equation. It tells you you need to understand the area of the base metal that is subjected to shear yielding and the area of the base metal that is subjected to shear fracture in order to calculate the strength. So it requires you to interpret what's going on. But now you understand what is the base yielding limit state, and you also understand what is the base shear fracture limit state. One has got to do with yielding occurring across the entire cross section. The other has got to do with this gouging of the material associated with base metal shear fracture. Good? Those were all the details that you needed to know about weld design. We've also talked about L minimums and A minimums. So when you look at the notes that I've already uploaded, it talks about A minimum, it talks about A maximum, the minimum length of weld Lw, and then it shows you a simple calculation for an example, which is just a 4 by 3/8 inch bar that is being designed to carry a certain load, ends up with the whole longitudinal and transverse welds. All of this information is available to you. You can take a look at it. And I would like for you to particularly take a look at this diagram, which talks about how fillet welds are to be specified. They are always specified with a right triangle, with the vertical leg of the triangle to the left, and the size of the fillet weld is rotated right next to it. The length is on the other side. These are two-sided fillet welds.